Petroleum Engineers Association. I'm Hesham Mokhtar, Senior Reservoir Engineer from Cairo, Egypt. So in this webinar, in this workshop, actually, we will highlight more interesting issues regarding PVT data analysis, PVT experiments, lab experiments, and also PVT data quality check and control. So let's start directly with the agenda of this workshop, the applications and the importance of PVT or reservoir fluid data, and the workflow analysis of reservoir fluid and reservoir fluid properties. Main issues to characterize different types of reservoir fluids and how to identify the reservoir fluid based on the production data and PVT data composition. Lab experiments actually will be highlighted in this workshop very quickly, and PVT workflow and an overview of equation of state modeling, and the most important part, which is the PVT data QA/QC. So as the traditional overview of any reservoir or petroleum engineering, so it's a branch of petroleum engineering that's concerned with the applications of fluid flow in the porous media during the development or production of the oil and gas reservoirs. To actually the main objective or mission of all oil and gas industry worldwide is to achieve the highest or the ultimate economic recovery, which means is to recover the maximum oil as much as we can at the lowest operating cost and capital or economic level. So such an examples of activities including is to identify how much oil and gas is originally in place in this part specifically. PVT data will be used to calculate how much oil or gas is initially in place, how much oil can be recovered based on the recovery factor and the reservoir pressure and driving mechanism and so on. The different how to identify the reservoir driving mechanism and the reservoir energy, how to predict the future production performance and production rates, and how to increase the ultimate recovery based on secondary or tertiary recovery techniques. So again, how does it work? Actually, in the subsurface, we have two major components in the grains or the rock board and pore spaces. So in the pore spaces, as you know, we typically have at the microscopic scale of the petroleum reservoir. Let's say you have such sandstone or clastic lithology or grains. In the pore spaces, we have a mixture of reservoir fluid, maybe water and hydrocarbon. The hydrocarbon may be oil or gas, or mixture of three phases: oil, gas, oil, and water. So the major fundamentals of reservoir engineering applications generally are dependent of three main concepts. The first, which is Darcy's law, because we have the fluid flow in the porous media, so Darcy's equation will be applied. Second concept is the material balance equation or continuity equation, which means at specific time, what a specific pressure, at a specific reservoir pressure, the remaining volume in the reservoir will be the initial volume minus the produced volume. So the concept and the most important concept and our interest on this in this course is, which is the PVT properties or equation of a state model. That means the reservoir fluid properties like oil density or viscosity or formation volume factor and solution gas oil ratio and so on. All of these properties are functions of pressure. So let's imagine in this 3D section of the reservoir, the pressure will decline from the average reservoir pressure and at the reservoir temperature to bottom hole flowing pressure. We have set of wells uh, up to wellhead pressure. So it's important to characterize fluid properties as a function of pressure using PVT experiments or equation of a state model. Accordingly, for complete system analysis, we may integrate additional two models, IPR and VLP model. So this is an overview of the production system. As mentioned, we have a set of wells, some may be producing natural or artificial. The production will be based on the reservoir driving mechanism and the reservoir pressure. The fluid and will flow in the porous media to the bottom of wells up to a wellhead or the choke, then to the production of different wells will be directed to the production manifold. Then to the oil and gas separation unit or two-phase or three-phase separation, and oil will be directed to storage tank after specific processing steps based on the fluid properties and the fluid composition and so on. So actually the fluid is reservoir fluids are available on all segments of the production system in the reservoir itself, in the pore spaces, in wells and on the surface pipelines, and also in the processing facilities, and also in the fluid will be directed to the final terminal to production, the pipeline transportation or and so on. So characterization of reservoir fluid is important and very critical to understand the major factors that will affect the production performance and the design of all of the segments of the production system, including the tubing design, casing and design, wellhead pipeline design, and so on. So the reservoir system, as mentioned, we have two major components, maybe rocks or fluids. So let's look at this part, fluids. Water actually is available in all petroleum systems, as we typically have, let's say, connect water in the oil zone, and then we have water production after a specific period of production of oil. The water may be increasing with time and so on till water peaks. So for the hydrocarbon part, we have oil or gas or based on the reservoir fluid type. So it's very important to identify the type of fluid composition, and also fluid properties. Typically, the most important property of liquid is the B sub O, or oil formation volume factor, and also solution gas oil ratio. Additionally, different flow assurance parameters are critical to identify, to study the reservoir fluids, like the wax content, asphaltene precipitation, the content of HTS and its effect on the pipeline or tubing or tubular design, and so on. So for gases, the same parameters will be required to characterize fluids, and also to design and plan the field development plan. So also the fluid characterization is an important part of the entire reservoir management process, in addition to the geological modeling and rock characterization. So this is an integral part. Also, all of these inputs will be directed to the 3D reservoir modeling to get the different reservoir management scenarios, or the FDP or field development plan. So reservoir fluids, as mentioned, we have a mixture of water and hydrocarbons, maybe oil or gas or both. The major relationship to study reservoir fluids is PVT, or three parameters will be included: pressure, volume, and temperature, to to relate the reservoir volumes to surface volumes, because actually we on production the fluids will be migrated from reservoir pressure and temperature to surface pressure and temperature. So we may have mass losses from liquid, including the release of solution gas and so on. Also, the characteristic parameters of the liquid or fluid, like viscosity, which is very critical for secondary recovery applications like water injection. Viscosity is very one of the critical fluid properties to study or expect such problems in water flooding or water injection, like the viscous fingering and so on. Also, gas solubility, density and compressibility, and also formation volume factors. So the simplest form of hydrocarbons actually is the we have set of organic compounds. The hydrocarbon are made of actually a set of hydrogen and carbon atoms associated together based on a specific structure. So in the basic building block for hydrocarbons, we may have one carbon atom and two hydrogen atoms, and based on the structure, we may have different hydrocarbons like methane, ethane, propane, and so on. Other hydrocarbon forms like let's say we have a chain between 5 up to 9 carbons. We have gasoline. If we have set of a dozen of carbon, we have diesel and so on. So based on this structure of between and number of carbon atoms, we have different forms of hydrocarbons. We have set of hundreds or even thousands of carbon and hydrogen atoms. So we have the plastics or polyethylene and so on. So as mentioned, the simplest form of hydrocarbon is the paraffin series, chains of carbon atoms and attached with hydrogen, like C1H4 or C2H6 and so on, methane or ethane. And also this is the typical chemical form CnH2n plus 2. Based on this, the composition of the fluid and the structure of this paraffin series, we have different types of hydrocarbons, from dry gas up to heavy oil or even tar and so on, based on the fluid composition in terms of C1 up to C7 plus, or the heavier components of the system. So this is the more complex structures like naphthalines or benzenes. This is the other structures of hydrocarbons. So the petroleum fluid phases, let's define some basic definitions. The phase is a homogeneous and physically distant part of the system, like oil phase, water phase, and gas phase, and so on, which is separated from other parts. Like we have clear gas oil contact, oil water contact, and so on. The equilibrium is a condition that means that we have the components of the system are in rest, no change in phase. Components, let's say C1, C2 into like H2S, carbon dioxide, hydrogen sulfide, and so on. Every one is one of them is a component of the system, which is a consistent part of the system. So to study the reservoir fluids, as mentioned, we have two ways: is to keep the temperature constant, which means we have isothermal system, and study the relationship between pressure and volume, which is the commonly used approach. We consider the reservoir is an isothermal system and keep the temperature constant. We may apply the studies the relation between the pressure and temperature and keep volume constant, but this approach is the widely used. Applications of reservoir fluid data actually including all parts of the petroleum system, from the miscibility studies, and also for gas condensate, reservoir condensate blockage effect, and gas cycling. Also, reservoir simulation, the PVT data are critical to define the type of fluid model, maybe black oil or compositional model. Also, flow assurance applications for the fluid. The flow assurance, by definition, is to ensure the productivity and operability of the fluid. That means is to eliminate such problems like hydrate formation, wax precipitation, asphaltene deposition, and so on. So all of this, and also applications of reservoir fluid data. Additionally, the study of simulate the production above and below bubble point or saturation pressure, which is the standard PVT experiments, the flash or CCE, differential evaporation, constant volume depletion, CVD. The fluid composition is very important. Also, the miscibility or slim tube testing, and so on. Or other thermodynamics is to study or to generate the phase behavior, or to study the other to generate an equation of a state model to characterize fluid, and also the volumetric parameters of the fluid are very critical, like the shrinkage of oil, or in other words, the oil formation volume factor. Also, the gas solubility, or RS, or gas oil ratio, and so on. So all of these are applications of reservoir fluid data. So specifically, fluid data are important for drilling to design well construction. Let's say we have H2S in the fluid composition. Also, in the to study the oil bismuth contamination. For reservoir engineering, actually, reservoir fluids are critical, and one of the major inputs for all reservoir engineering studies and reservoir engineering applications, like the material balance analytical reservoir modeling, reservoir simulation and reserve estimation, well testing interpretation, and also other applications. For completion, the design of completion design, artificial lift calculations, and artificial lift design, subsea applications, all of them are dependent of the fluid data. And for production, also production logging and production forecasting and multi-phase flow metering are dependent of the type and the characteristics of the fluid. So fluid characterization study is starting with real-time monitoring and reservoir fluid sampling based on the formation tester technology or wireline tools. Once the sample is collected, we can collect sample or bottom hole sample at a single phase condition at above the saturation pressure, and then the sample will be directed to PVT laboratory for lab experiments and flow assurance analysis. So as an importance of an example of PVT data application is the calculations of original oil in place or stock tank oil initially in place is calculated, as you know, using this a standard equation as function of the above volume, oil saturation, and this term which is PVT parameter, oil formation volume factor at initial reservoir pressure. In this example, this is the correct initial oil formation volume factor 1.48, but let's assume it's wrongly evaluated as 1.45. So the error in this error in PVT data will actually lead high or much error in reserve calculations by about 60%. So that's why the PVT data are critical and very important for different petroleum engineering applications. Also, for condensate reservoirs, we typically have in the region near the wellbore, we may have the condensate banking or condensate blockage around the wellbore due to the reduction of average reservoir pressure below the dew point pressure. So this region will be highly saturated with the condensate liquid, which may use the blockage of gas production or complete shutting of the well. So this phenomenon is also important to be characterized using PVT experiments. So in this case, the possible scenarios to resolve this issue is gas recycling or even the hydraulic fracturing to improve the mobility of the gas in the near wellbore region. Also, other flow assurance applications like in case of we have hydrogen sulfide, we have to consider this for the planning and the material selection for production and processing, and other like the organic scales like asphaltene. In this case, we have to consider the asphaltene dispersant in the system. So the general workflow for PVT is sample at the bottom hole or even at separator condition, sample validation to check the integrity of the sample and also to check the cleaning of sample. If sample is clean or contaminated with the drilling fluid, specifically oil-based mud, and prediction of phase behavior based on composition and flow assurance parameters. And last step is the simulation based on a specific equation of a state. So as an application of reservoir fluid modeling and reservoir simulation, PVT is important to apply mass balance in the simulation equation and to convert the bottom hole volumes to equivalent surface volumes. Sources of PVT data can be lab experiment, and then this data will be used to generate an equation of a state model, or even in if we have no available PVT data, we can use correlations based on a few inputs. But we have to check actually the quality check PVT data before developing the equation of a state model, or before applying specific correlations. So this is the general and standard BT diagram or phase diagram for reservoir fluids. If the reservoir pressure is located right here, we have dead or black or live oil system. In this side, we may have dry or wet gas at high reservoir temperature. But right here in the near the critical point, we have near critical fluids, let's say volatile oil or gas condensate reservoir. Simply, this is the bubble point curve, the curve separating between the single phase liquid region and two phase region, and this is the dew point curve separating this single phase gas region and two phase liquid and gas region in this region, and this is the critical point. So if the system is located in this side or this side, we may apply black oil simulation, but for gas condensate or volatile oil systems, we have to apply the compositional simulation using equation of state models. So simply black oil models is to assume oil and gas phases are represented by only one component, and accordingly we assume the system or composition of oil and gas is constant with pressure and time. So we have oil plus solution gas represented by RS and other component, which is the gas. But for compositional, the oil or gas phases will be represented by multi-component mixtures in because we assume pressure, temperature, and the composition are changing with time. So we have liquid phase and vapor phase. So Xi is the mole percentage of the liquid for all components, and Yi is the mole percentage of mole fraction of the component I in the vapor phase. So as a simple comparison between black oil and the compositional simulation, in black oil, we have PVT parameters like formation volume factor, solution gas oil ratio, and viscosity as function of pressure. But for compositional, we have the equilibrium ratio, Ki, and viscosity and density. All of them are functions of pressure and the mole percentage of liquid and vapor phases. So as a quick overview of reservoir fluid sampling, we have two main techniques, bottom hole and surface sampling. Surface maybe wellhead sampling, and widely used technique is separator sampling. But bottom hole sampling is to collect a fluid sample at the reservoir pressure and temperature. So bottom hole sampling is important actually if you need to ensure we have single phase sampling above the saturation pressure, maybe bubble point or dew point. Also to collect the sample at reservoir conditions, but the sample volume is typically limited from 400 up to 600 cc as the total sample volume. Surface sampling as we may collect samples from separator if we wellhead pressure actually above the saturation pressure. If you need to collect sample based on the accurate gas oil ratio measurements. Also, surface samples are important if you need large volumes of samples for specific studies like EOR studies, and also if we have high water cut, so surface sample is maybe sufficient in these applications. So the fluid behavior generally, let's say this is the pressure behavior and with distance from the well bore. So at pressure higher than the saturation pressure or bubble point pressure, we have single phase liquid or oil. Once the pressure average reservoir pressure is reduced below the bubble point pressure, so we have the solution gas will start to release out of the liquid. Once the gas saturation is higher than the critical gas saturation, so as the gas will start to move on the flow in the reservoir. In that case, we have two-phase flow in the reservoir, which means the mobility of oil will be maybe greatly affected by the flow of gas. For separator sampling, let's say this is the fluid well stream input to the separator, and this is the production, the water line or water drain in the bottom of separator, and the oil line. We can collect a separator oil sample from this oil dump valve, and from the gas outlet we can collect gas samples from this outlet. So sampling is very important is to ensure the separator conditions are stable to avoid any inconsistency in the calculated gas oil ratio before recombination of oil and gas samples. If we have actually 2 or 3 stage separation separators, in that case, the samples will be collected after the outlets of the high pressure separator. Bottom hole wireline sampling, one of the widely used techniques is the modular formation dynamic tester (MDT). it's a wireline tool. We have set of modules, let's say flow control module, optical fluid analysis, multi-sample chamber, and sample modules. The concept was to ensure the sample is at conditions higher than the initial or initial reservoir pressure to ensure single phase sampling. So let's say this is the initial reservoir pressure. The bottom of samples will be pressurized to pressures higher than the initial reservoir pressure to ensure actually the sample is single phase, even the pressure or the temperature of the sample is reduced, as the sample will be converted from bottom hole temperature to surface temperature. So in that case, even we have reduction in temperature in the sample will be in that case also at the single phase conditions. Simply, this is the configuration of wireline MDT tool. This is the inlet of fluid. The fluid will passes through the several modules, and we have resistivity cell or optical fluid analysis to differentiate between mud filtered and hydrocarbon or even water. And this is the bombing out phase. Once the fluid is the reservoir fluid is identified using the optical fluid analyzer, so we can collect sample using a multi-sample module. So the fluid will be diverted to this sample chamber by closing this valve after the process of bombing out. So actually the challenges in the bottom hole samples, maybe when we have tight reservoirs or a reservoir permeability is low or the fluid viscosity is high. So the solutions in that case is to increase the flow area of the sampling probe. This probe. So we have set of probes based on the flow area. So the largest flow area will facilitate accurate measurements of bottom hole pressure, and we can collect the bottom hole samples at low reservoir permeability or even at high or very high oil viscosity. Like this sample, we have a heavy oil reservoir, and we can collect the bottom hole sample. So in this video, as you can see, the process of bottom hole sampling, this is the wireline tool. This is, let's say this is the depth of selected sampling point. This is the probe. Once the backer is retracted, set the backer so we can collect samples, start draw down. The pressure is declining, as you can see. So while bumping out, and we can stop bumping to generate to measure reservoir pressure, and then we can collect sample after the sequence and the process of bumping out. So applications. So applications of high or large flow area of bottom hole sampling tools, like this oval shape probe. The flow area of available for the fluid is high, so we can collect sample faster, and we can measure pressure for low permeability reservoir, and also we can collect samples for very heavy oil systems. So this is the process of optical fluid analysis. Let's say in this, I will not go through in details for this in this workshop due to the time limit. But let's say this is at the start of pumping out, the complete system input to the bottom hole tool is water, identified by this OFA module of MDT tool. While sampling, while pumping out, we have clean oil and some batches of water or mud filtered, And while at sampling time, we have complete or 100% oil and very, very low or maybe no mud filter. This is at sampling time. So sampling technique is based on the type of the reservoir and the reservoir pressure higher or above or below the saturation pressure. I will go through in this slide quickly. So now, very important about which is PVT lab experiments. So the traditional or basic PVT workflow is after fluid sampling and sampling real-time monitoring and sample integrity and transportation, compositional analysis in the lab using zero flash testing, PVT experiments. It's important to check the data QC and also its pressure depletion experiment is to make a specific sequence of experiment by reducing the pressure step by step. And last step is to analyze data after quality check to generate the PVT model. So first, or the major lab procedures, as mentioned, the first is the compositional measurements, is to identify the mole percentage of vapor and liquid phases, YI and XI. Second is flash vaporization or CCE, constant composition expansion, differential vaporization or differential liberation, separator testing, and oil viscosity measurements. So, and the first step, as mentioned, is the validity check or check sample integrity. Once the sample is received at the PVT lab, the sample will be heated to the reservoir temperature and will be diverted to agitation to allow stabilization of the fluid in the sample. And then we will next step is to measure the opening pressure of the sample. So this is an example actual data for PVT validity check. Let's say this is the cylinder number of the bottom hole wireline sampling tool. This is the selected depth. Fluid type, let's say we have this one, we have oil. This is the sampling condition, reservoir pressure and temperature, and this is the laboratory opening pressure at reservoir temperature. It's actually within the range of the reservoir pressure. In other cases, the opening pressure may be higher than the reservoir pressure to ensure the sample is in a single phase condition. So this is the MDT sampling sheet, as you can see, for a specific well, and this is the PVT lab validity sheet for the same well, same samples. This is the serial number, bottle number, and depth. Let's say this this sample we have from MDT sampling sheet, first one. For serial number 1447, the flow type is oil and water. We have about 97% oil based on optical fluid analysis, and while at lab we have in this sample we have about 10 cc water, which means this is data is more or less accurate. But the opening pressure for this sample, as you can see, is 5,400 psi, but the reservoir pressure is about 3,150 psi, which means opening pressure in most of cases will be higher than the reservoir pressure to ensure the sample will be still single phase. So lab procedures, as mentioned, is to determine composition, shrinkage, recombination, and perform different lab experiments as a function of pressure. So this is the PVT workflow based on after validity checking, based on the fluid of reservoir fluid we have sort of the composition is major and important part of the PVT study, followed by the flash or constant composition expansion test, or PV, or pressure volume relationship, is also one of the major tests for all types of fluids. But based on the fluid for liquid, let's say black oil or volatile oil, differential liberation or separator testing and all viscosity are basic PVT workflow. We may apply CVD for volatile oil. For gas condensate, the same. We have CVD is very important. For wet or dry gases, the flash or PV relationship is sufficient, because we will estimate all of gas properties based on gas composition and the data from flash vaporization. So, a quick overview of different types of hydrocarbon or hydrocarbon classifications. As you know, we have typical 5 reservoir fluids, but for a general perspective, for reservoir fluid application, we have 7 reservoir fluids, including bitumen or heavy oil or tar, and this is the traditional reservoir fluids or standard reservoir fluids from black oil or low shrinkage oil, volatile oil, retrograde gas, condensate, wet and dry gases. This is the some of the basic characteristics of different types with ABI, viscosity, and or formation volume factor for different types. I will go through quickly with these slides. For bitumen, for heavy oil or tar, low shrinkage oil or black oil. This is the for volatile oil, and we have much gas in solution, and the formation volume factor will be much higher relative to the black oil. Additionally, the oil gravity or API will be slightly higher than the black oil. Retrograde gas condensate or condensate liquid, this is the major characteristics. API may reach up to 70 degrees. And this is the characteristics for wet gas or and dry gas. So simply the study of PVT is, let's say we have this PVT cell, we have single phase liquid at this point, and this is the BT diagram. This, as mentioned, bubble point curve, this is the TO point curve, and this point is the critical point. In this region, we have two phase system, oil, liquid, and vapor. So at this point, we have single phase liquid at the PVT cell at the reservoir, same reservoir temperature and the initial reservoir pressure. At this point, this is the bubble point curve, which means the first bubble of gas will be appeared. And once we have additional reduction in the pressure, so we have much gas will release out of liquid. So in this at this point, we have 40% liquid. But right here we have the system is typically 100% vapor at the dew point give, and also one last droplet of liquid. Right here we have 100% actually. The system is entirely vapor or gas. This is simply a BT diagram and how to study the PVT data based on this hydrothermal process. Keep the temperature constant at the reservoir temperature. In this process, actually, while measuring pressure and volume, we will measure other physical properties like formation volume factor, density, viscosity, gas oil ratio, and so on, and also the composition of vapor and liquid. So characterization of fluids will be based on actually the initial pressure and temperature, or maybe based on production performance or the fluid composition. So for this is the crude oil and gas. This is all types of gas and all types of oil as mentioned before. So as for standard PVT or pressure temperature or PVT diagram, this is the different types of system. In this, in the right hand side of the critical point at temperature less than the critical temperature, the system is oil, while on at temperature higher than the critical temperature, the system of is gas. In that case, and the type of fluid specifically will be based on the location of temperature of the system. Right here we have gas condensate system between the critical point and the pre-condensate temperature. So by the way, this is the maximum temperature we can have the two-phase fluids, and at temperature higher than the pre-condensate, the system is entirely single-phase gas or vapor. So as mentioned, we can identify different types of reservoir fluid based on the phase diagram and the location of the reservoir pressure and temperature relative to the critical point. So this is, we have black oil. If the system is close to the critical point, we have volatile oil, and between the critical point and pre-condensate, we have gas condensate. If the temperature higher than the pre-condensate, we have wet gas, but in that case, the separator condition may be in the two-phase region. If the system entirely at reservoir temperature and separator condition higher than the outside the two-phase region, we have the dry gas. So it's very important to get the changes or differences between the phase diagram and the ternary diagram. So all of these two different types will be used to define and show the shape and size of the two-phase region. This is the two-phase region using the phase diagram, and this is the two-phase region using the or three-phase region or multi-phase region using the ternary diagram. So phase diagram, it's a pressure temperature curve, which means pressure temperature relationship. In that case, the composition will be constant as a function of pressure and temperature, while the ternary diagram, the pressure and temperature will be constant, but we will change the composition. So it's a graphical display of three component system, let's say C1, C, and other components like C4 and C12, and like light, intermediate, and heavy component mixture, like let's say for miscible flooding applications. And the entire ternary diagram will be a snapshot at constant pressure and temperature. This is the general guidelines for characterization of reservoir fluids, as you know, as function of composition and other parameters like API and gas-oil ratio trend. And this is the standard schema and guidelines defined by McKean using production and data and lab experiments as initial producing gas oil ratio and stock tank oil gravity API, and for lab the phase change in lab also at for black oil system phase change at bubble point, but for retrograde gas condensate the phase change at the dew point. Also C7 plus in mole percentage is another indicator for the reservoir fluid type, and in this direction the amount of C7 plus 15 plus in the well stream will be much lower relative to the black oil. So oil and gas properties, we may have some flow properties like viscosity for the oil or gas, volumetric properties for the oil system, volumetric properties Oil formation volume factor is very important and very critical, specifically for volumetric calculations and reserve estimation. Solution gas oil ratio, total formation volume factor, and also oil density. Unique properties like the specific gravity, API, bubble point, and other similarly different equivalent properties for the gas, like gas compressibility, Z factor, and gas formation volume factor, and also apparent unique gas properties, apparent molecular weight, pseudocritical pressure and temperature, and so on. So compositional measurements as the first step of PVT lab experiments is to start using a zero flash test. The sample will be converted from reservoir pressure and temperature to a standard pressure and temperature in a single step, which means we have two components, flashed gas and stock tank oil. So the flashed or stock tank liquid will be analyzed using a liquid injection gas chromatograph equipped with what we call FID flame ionization detector. So the process is based on selective separation of individual components of the system as long as the temperature is increasing in a column. The capillary column is included in this chromatograph apparatus. It's within 30 meters long and within 500 micron diameter. So we have also the sample is injected to once the sample is injected to the gas chromatograph will be followed by carrier gas like helium or nitrogen or inert gas. So as temperature is increasing, so the lighter components will be separated from the system, and other heavier components step by step will be separated. So we can identify different peaks for every component using the gas chromatograph. Liquid composition actually is carried in two steps. Up to C9, C10 plus, and other non-hydrocarbon compounds like nitrogen or CO2 using the capillary column chromatograph. And for heavier compounds, we may use mini distillation apparatus. So for the flashed gas, additionally, we have thermal conductivity detector in addition to FID, the flame ionization detector. So this is the for gas, the gas composition will be entirely carried out using the capillary column chromatograph apparatus. This is the concept of chromatograph as mentioned. It's the detector response against the retention time. So let's say at lighter components will be detected at first out or at low temperatures like nitrogen followed by methane, CO2, and then ethane peak and so on. So the most lighter components will be identified at first or at low temperatures, and the heavier components will be identified or detected at a much retention time or at much higher temperatures. So in this video, as you can see, this is the gas chromatograph concept. This is the sample and injection mode, and this oven the temperature is increased, and with these steps, we can identify different peaks of the components like C1, CO2, N2, and so on, up to the more heavier components in the system. Again, this injection mode in this column, capillary column, the fluid temperature in the stream is heated step by step. So we in the compositional measurements, when we have the mathematical or physical recombination based on the mathematical assembly. We have average gas oil ratio from the field production data, but for physical recombination, we must have field measured gas and oil rates, and we must correct it using gas gravity and compressibility factor. For the oil phase, we have to have the shrinkage factor of the oil. So well stream composition, Zi is the mole percentage of the well stream is calculated using this equation. Function of Xi is the liquid composition in mole percent or mole fraction in this equation, and Yi is the vapor or gas composition, and this term, which is total mole fraction of the well stream, defined using this equation. So this is the calculation of the fluid composition in PVT labs. So this is the compositional data. We have components, let's say N2, CO2, C1 up to let's say C7 or C30 or C36 and so on. The composition will be presented initially as a weight percentage, and then when using the molecular weight and specific gravity of all components, we can have the composition in mole percent. Accordingly, we can convert this composition into mole fraction. So the QC of composition, the widely used technique in the oil and gas industry is Hoffman. Which is technique is to plot log of K values, the equilibrium values against a component factor Fi. This for stable separation for every component. So using the chromatograph, we have to have straight line. So in this equation, as you can see, we have log KB against F factor or component factor. This is an actual PVT sample. So we have actually a straight line with good fitting for this line, 0.96, and another sample we have a higher quality of using the QC using Hoffman plot. So the concept is the lighter components up to C6 must follow the straight line, but the heavier components may have such deviation for the heavier components. But if we have higher deviation from the straight line for even the lighter components like C6 or C5, in that case, we have to repeat or recheck the compositional measurements. This is an example of different fluid samples, and we can identify the good data and important or critical data from simply from fluid composition. Let's say in this fluid we have significant amount of H2S in moles, about 3 mole percent, and also C1 methane is about 13%, but C7 plus, as you can see, is about 62%, which means we have actually black oil, or even maybe in the margin with the heavy oil. API is about 25 degrees. But for this one, we have no H2S, which means it's a good news, because H2S implies additional cost in the processing and transportation facilities and so on. C1 is about 37 more percent, and C7 plus is much lower relative to its sample. So fluid system in that case is volatile oil with about 38 degrees ABI. This is an example of the entire fluid composition data. This is the components, and this is the components from C7 plus up to C36. And this is the lab results: molecular weight, gas density, liquid density, and this is the composition in mole percent. So for C7 plus, we have to the lab PVT must define the mole percentage, molecular weight, and density for C7 plus components. So flash or PVT PV relationship pressure volume. It's simply as mentioned before, all PVT experiments are carried out at constant reservoir temperature, which means the system is isothermal. So the PVT cell is defined using specific weight, starting at pressure at initial reservoir pressure or at pressures higher than the initial reservoir pressure and the reservoir temperature as mentioned. So the measurements in that experiment is simply we will calculate the VT or total cell volume as long as we decrease the pressure step by step without any release of gas. So at pressure higher than the saturation pressure, no gas will come out of liquid. We have single phase liquid, but at this point, at this pressure specifically, we have much increase in the total volume, and at pressures lower than this value, we have the some release of solution gas out of liquid phase, which means the pressures right here in step 3 and step 4 are less than the saturation pressure. One of the QC is to for flash vaporization is to check the stability of pressure for every step in the flash experiment, and then using VD we can calculate relative volume. It's VD total cell volume relative to the volume at saturation pressure. Simply, we will plot the volume or relative volume against the pressure. We have to have two straight lines with different slopes, which means at this point we have much increase in the total cell volume due to the release of gas below the bubble point. So VD is much, we have much increase in total cell volume less than the bubble point pressure. So using VR, the relative volume, we can calculate actually the oil compressibility using this equation, and we can also identify the bubble point pressure for the PVT system. In this animation, as you can see, we can this is process is simplified. So reduce pressure still above the bubble point. Once the gases appeared at the bubble point, we have the change in the slope of this line pressure volume relationship. Again, above the saturation pressure, no gas, but within the pure saturation pressure, we have much increase in the total cell volume due to the release of solution gas. You have to keep in mind this valve is closed, which means the gas will be always in contact with the oil, which means we have constant composition expansion or constant mass expansion, which means no change in composition with pressure reduction. And this is the process simply step by step. So this is the typical results from flash or CCE or CMD experiment pressure against the relative volumes, and this is the Y correction I will highlight in this QC parameter. So this data, so at the relative volume at the bubble point is equal 1 because relative volume is VT divided by VB or V at saturation pressure. And this pressure highlighted in red is the initial reservoir pressure, but the experiment may start at pressures higher than the initial reservoir pressure. So in that case, we have what we call Y function. We have to define relative volume data and smooth data below the saturation pressure, maybe due to the lab inconsistencies, to measure the total volume below the saturation pressure. Y function simply is a dimensionless compressibility functions to smooth the relative volume data. This is the Y function is defined using this equation: function of pressures and volumes, saturation pressure and volume at the specific at this pressure, and volume at the relative volume. So we will plot Y function against the pressure and get the straight line on fitting for this equation and get the equation parameters. Then we can recalculate the relative volume below the saturation pressure using this formula. Just an example of Y function, as you can see, as a QC for the flash vaporization data, we have perfect equation or matching, which means it's a good indication for the quality of flash vaporization for this well. Another well we have this is, as you can see, the ranges of pressure. It's from 600 psi, but which means it's a low pressure reservoir. But this one we have high pressure reservoir, and the QC parameter of Y function. Another comparison between heavy oil and the black oil. This is the relative volume against pressure, and it's using in the heavy oil. As you can see, we have clear a change in the at the bubble point or saturation pressure, which means this is the above the saturation pressure, no change in the total cell volume, but below saturation pressure, the relative volume is increasing at high percentage. But for the black oil, we have actually the bubble point maybe not clearly identified due to the the expansion of oil above the saturation pressure due to the high amount of solution gas. Second important DV or differential vaporization experiment. Simply, once the bubble point or saturation pressure is identified using the flash or CCE experiment, same concept is to start at keep the temperature is constant at the reservoir temperature and isothermal as an isothermal system. Started from the bubble point, and measure oil volume. Once the pressure is reduced, so we have amount of gas that will be released out of liquid. So, and this step, the gas will be removed in this step, and additional step to reduce pressure and so on. So the concept is to vent all, remove all this gas from the contact of the oil and reduce the pressure successively up to the standard pressure and reservoir temperature. So this is the procedure of differential vaporization. In all of these steps, we will measure the gas volume, gas properties like gas viscosity and gas density, gas formation and volume factor, and also gas composition. And the process will be repeated up to or down to the standard pressure at reservoir temperature. So the volume right here is VR, or the residual oil volume. So in this animation, similarly, this is the procedure of differential vaporization. So as you can see, this valve is closed, starting at the bubble point pressure, as you can see. So once the pressure is reduced, we have gas. So we will open this valve to vent all of this gas and close the valve, successively reduce the pressure as a second step, and vent all of the gas, and so on. This is the simply the process of differential vaporization experiment. So the gas will be removed in the contact of the liquid. So simply, flash is to simulate the production process above the saturation pressure, or even if the gas is still lower than the gas saturation is still lower than the critical gas saturation. In that case, the gas is simply in contact with the oil, which means the process of flash vaporization. But differential vaporization, on the other hand, we once the gas saturation is higher than the critical gas saturation in the reservoir, so this gas will be able to move and flow in the reservoir, which means we have two-phase flow in that case. So the gas will move in will be and will be not in contact, in direct contact with the oil. Maybe the gas will be directed to the production wells, or this gas may attach or move up structure to join an existing gas cap, or to generate a new or secondary gas cap. So that's why this is the process or procedure for flash and differential vaporization. So final PVT data will be an integration between flash and differential vaporization data. This is the data from DV experiment. It's the pressure starting from bubble point pressure, measure gas removed in CC and at the standard condition, which means at standard pressure and temperature. This is the oil volume in CC and the incremental gas incremental gas gravity increasing step by step, because the heavier or intermediate components of the gas will be released at the last steps. So the gas gravity is increasing at steps of lower pressure, and the last step, as you can see, we have zero pressure in BSI gauge at reservoir temperature, and same pressure, but keep or let the PVT cell to be cooled down to the surface or standard temperature 60 degrees Fahrenheit. So this is simply the DV data, and as you can see, this is the all of the removed gas in standard cubic foot from the PVT cell, and this is the oil volume at zero pressure and standard temperature, or at standard conditions. And this is the gas volume and incremental gas recovery, and so on. So, and at zero pressure, we have no gas in solution, which means RS is equals 0. And this is the raw data. We can calculate the V gas relative to the residual oil, and accordingly we can calculate the oil formation volume factor and solution gas oil ratio using these definitions. This is another example of actual PVT data. In this sample, we have all parameters: solution gas oil ratio, relative volume, relative total volume, oil density, Z factor, and incremental gas recovery, and so on. For more details, the DV or DL, differential liberation oil property table, as you can see, this is the we can measure API and total and also the relative and the density at standard conditions. Similarly, for gas property table, we can calculate all of these parameters against pressure up to the standard pressure 14.7 psi absolute or 0 psi gauge. Additionally, this is the standard or final data you can receive from PVT lab from differential liberation experiment. Again, we have pressure against oil and gas properties, oil density, oil formation volume factor, the solution gas oil ratio, oil viscosity, and so on. Similarly, gas gravity, Z factor, and gas compressibility and gas viscosity, and so on. The next experiment lab experiment, which is the separator test, simply starting from bubble point at reservoir temperature. So this is the volume of this liquid. This liquid, once we can reduce the pressure and temperature to first stage separation. So we have right here the set of this liquid will be separated to main components, liquid and gas. If the next step is the stock tank, which means another pressure and temperature, we have V2 of the gas and L2 for this liquid. So L2 at stock tank barrel, but this volume is, which means at the reservoir at bubble point and the reservoir temperature. So the volume is at using units in the reservoir barrel, not stock tank barrel. So we can calculate our formation volume factor. It's the volume of at reservoir condition relative to stock tank volume L2, and the similarly the solution gas oil ratio, the total gas in solution V1 plus V2 relative to the stock tank liquid. So actually the objective of the separator testing is to characterize the fluid behavior by changing the pressure and temperature, and also optimize separator conditions to achieve the maximum liquid recovery, which means is to achieve the highest API gravity and lowest solution gas oil ratio. In this animation, as mentioned, you can highlight the separator testing. We have the stream, liquid stream. This stream will be separated to parts oil and gas. For second, this is the second stage. Much this liquid will be separated into two main components and so on. So this is the standard results of separator test. We will and we need to identify solution gas oil ratio, API and oil formation volume factor. So the objective is to optimize the separator condition by maximizing the API and maximizing liquid recovery of the separator. This is the assembly of separator results. This is the optimum condition, which means we have highest API, lowest solution gas oil ratio, and lowest oil formation volume factor. So this is the optimum separator first stage separator condition. It's 100 psi gauge. This is the parameter we can control to optimize these separator conditions. Last part of the lab experiment, oil viscosity measurements. Simply, the viscosity measurements is calculated in this apparatus, which is rolling ball viscometer. In this, the concept of this actually is the capillary, or similar to the capillary viscometer. So it's designed to simulate the differential liberation experiment. So the process is to calculate or measure the time taken by a ball to travel through this barrel of this at different angles. So we will change the angle of this apparatus based on a specific design and specific procedure. This time will be converted to equivalent the fluid viscosity using specific equations based on the calibration of this the rolling ball viscometer. So now I will highlight very quickly phase behavior simulation. So using PVT lab composition and PVT properties, we can input all of this data into equation of state model, and then we can predict the performance under different production processes. We have to calibrate and QC the PVT data, and In that case, once the data is checked for consistency, so we can calibrate the equation of a state model. This is simply the PVT modeling simulation. So I will go through this is the highlight of equation of a state, starting from the Boyle's law and combining this to get this equation, ideal gas law at specific assumptions. And equation of a state, this is a general equation of a state, which means it can be presented as a cubic form, which means a cubic equation of a state. We have parameters A and B, which is a function of pressure and temperature. So the physical solution of this equation, we have the minimum and the maximum relative to oil and gas or vapor phases. So we can get the volume in the right-hand side, and we have engine. We can get this different forms of equation of a state and get parameter A and B. So the widely known and commonly used equation of a state and one of the oldest equation of a state, Van der Waal equation in this form. We have parameters A and B as some assumption and consideration parameters for attractive forces between molecules and the volume parameter. So this parameter, this equation can be defined in this cubic form in form of volume, and accordingly can be presented in the form of z factor to be in the cubic form or cubic equation of a state. This is the history of equation of a state, as you can see, starting from 1662 up to this is the 1982 Benelux equation of a state, which means we have volume correction factor to this is the one of the widely used equation of a state. Others like BR or Bing Robinson two parameter equation of a state, and others like the SRK equation of a state. This is the one of the two widely used equation of a states in oil and gas industry. So tuning of the equation of a state is to, or the specific workflow is splitting C7 plus characterization using specific pseudo components, and also grouping. And then once the fluid is characterized, we can lump or group to reduce number of pseudo components and reduce the calculation time for simulation applications, for example. And this is a fine tune is to match lab experiments. So the process is to match lab experiments by changing some of the equation of the state parameters. So we have to ensure, we have to consider, we have to understand the importance of PVT QC and PVT quality control before defining or before generating the equation of a state, because we will modify some of the equation of a state parameters to match the lab experiments. So this lab data must be consistent, must be accurate, and must follow a specific criteria. So matching equation of a state to match lab experiment, actually equation of a state are not truly predictive because we have some errors in saturation pressure and some errors in density and so on. So you have to QC and check the lab experiments before generating any equation of a state to generate as a consistent PVT model. And this is the applications of equation of a state to predict composition, specifically for composition and simulation, gas injection, combination design, and so on. I will miscibility parameters, and I will not go through in details in this, but now I will highlight PVT data QA QC. So starting with, actually we have several publications to highlight the QC and the quality check of PVT data. This is some of these examples and important papers. So the general PVT QC workflow is to check the sample integrity and then check the consistency of lab experiments. So first step is the validity check, contamination check to check the sample is not contaminated with oil-based mud. Composition check using, let's say, Hoffman plot, separator test check, and then CCE and differential liberation check. So as mentioned, we have two major steps to check the integrity of the sample and check the procedure and consistency of lab workflow. So leakage and contamination, then the sample variety, and then the composition separator, flash, and differential vaporization. So as mentioned, the validity check is to check the opening pressure of the sample must be at the must equal or higher than the initial reservoir pressure to avoid the sample is not located in the two-phase region, and ensure we have single phase fluid at the PVT lab. Second is contamination check as to ensure the sample is not contaminated by oil-based mud or diesel. This simply can be generated using the fingerprint of oil and the oil-based mud or diesel. And in this example, we have this is the well stream of this sample, and this is the contaminated sample, and this is the in the red color we have the phase behavior, the fingerprint of the clean sample by excluding the effect of the oil-based mud. Now this is the composition check as mentioned. It's the using this material balance, using this equation, we can plot yi divided by zi. So yi is the mole fraction of vapor, zi is the well stream composition in mole fraction or mole percent, xi is the mole fraction or mole percentage of liquid. And this criteria, if we plot this parameter against using this equation on y-axis against this parameter on x-axis, so as long as we have good matching and good straight line, which means we have good compositional data and more consistent data before using the compositional data. Additionally, we can calculate using the slope of this line the GOR from this QC workflow, and compare this GOR with the flash GOR from the PVT lab, and calculate the error. So if the error is more or less 6%, so the lab is the compositional data are valid. Also, this is the another separator test check, which is Hoffman check, as mentioned before, as to plot Hoffman factor on X against the log the equilibrium ratio on y-axis. So in this technique, we have to have low deviation from this straight line for the heavier components like C6 and C7 plus. But as long as this heavier component follows this straight line, so the sample is valid. Another technique, which is Buckley check, is to plot this. Let me log K against the critical temperature squared. So as long as we have a straight line, as mentioned, you have an equilibrium between liquid and gas phases as from the separator test as a QC for separator testing. Also for CCE test check, stow plot relative volume against the pressure. This is the determination. We have significant changes in the slope of two lines at the saturation pressure, specifically for black oil or heavy oil reservoirs, and also to check to plot Y function and check the this straight line. So as long as we have good straight lines, so the equilibrium between the oil and gas for every step, for every pressure step in the CC experiment is now is valid, and results are consistent. Differential liberation step. The first step is to check the material balance check. The concept is the mass of the sample and or the released gas or the evolved gas at every pressure step must equal the sample mass or the sample weight at the pressure higher than the bubble point pressure, which means simple material balance concept. Set of calculations will be applied in this and differential liberation, and at the end we will check this error as a percentage, as long as the error is less than 0.1. So the material balance check is valid, and it's very common to have much high error at the last step, which is very common. So now the material balance check is valid for this differential liberation experiment. Additionally, it's important to plot the vapor composition against the pressure. So the behavior of all components must follow a monotonic trend like this, but we may have some inconsistency for lighter components like C3 or C4. It's very common, but generally we have a monotonic trend of vapor composition against the pressure. This is the mole percentage against the pressure step by step. Also, the yield viscosity against the pressure is to check this inflection point at the bubble point. So the standard behavior of oil density or viscosity, as you can see above the bubble point, we have expansion of oil without release of the solution gas. So oil viscosity, oil density is decreasing with pressure, decrease, but higher, lower than the bubble point pressure, the density or viscosity in similarly will start to increase, because we have the solution gas will be released out of the liquid, which means the liquid becomes more viscous and more denser due to the release of solution gas. Last step is to check the fingerprint plot for different samples if applicable, and compare between the mole percentage against the composition of different components in the reservoir. The sample in the green color we have, it's not following actually the trend, the entire trend of this system. So we have such inconsistency in this sample. Is done another QC for the PVT experiments. So now this is the evaluation criteria for bottom hole samples, as you can see, and this is the accepted deviation in as a percentage for gas oil ratio, stock oil density, plus fraction density, and so on. And this is the another evaluation criteria for separator samples and for different parameters. Actually, all of these details will be highlighted in much time in the upcoming course. So finally, as once the PVT data and lab experiment data is evaluated and the quality checked, and we ensure we have consistent PVT data and consistent lab experiments, so now we can go to equation of state tuning by changing some equation of state parameters like the critical pressure temperature and the eccentric factor for the heavier components, heavier than C7 or C6 and so on. And also if we have such the significant non-hydrocarbon compounds like CO2 or N2, nitrogen or carbon dioxide, so we can change the sum of the KIG, which is the binary interaction coefficient between these parameters and different components in the fluid system. Actually, this is the message we need to deliver today. That's this is the PVT data for tuning against the pressure. We have much deviation from lab experiment, and this is the PVT data after tuning of the equation of state. We typically matching the lab experiments. That's all I have in this session. Thank you so much, and feel